Hello guys, welcome to the week 4 content. So this week we'll be covering the optimization thing, gradient descent, control map, accelerated gradient descent. So I hope that all of you have went through the content. So like the previous weeks, I will be just brushing up the concepts which are covered in this week, and then we'll be solving the last year questions. So let's wait for 1 2 minutes for people to join. Okay. Yeah. So welcome guys. So for the this week content, as I mentioned that we'll be covering the week 4 contents. And the first thing I will be discussing is about the contour maps. We'll be talking about the losses, that is the L2 loss, Gaussian-Toppi loss, and the stuff. Then we'll be discussing one of the important things, that is the optimization. That I guess we have already seen what is the gradient descent. We know that about the gradient descent, we need to make sure that at each and every point we are making sure that a function is decreasing. So it's basically like that we are constructing a loss of sequences loss. We want to L1 should be greater than or equal to L2, like it should be. So in the last loss, we are as minimum as possible. So that's the normal optimization technique. There's a bunch of varieties of the optimization algorithm which are covered in this week content. So some of them are the momentum-based gradient descent. We are having Nastov accelerated gradient descent, stochastic and mini batch gradient descent, and Adam gradient descent and RMS prop, Adagrad. So I guess bunch of optimization algorithms were discussed in this week. So firstly, we'll be going through the varieties of the optimization algorithms which are covered in this week content, and then we'll be moving for the then we'll be moving and solving the problems for the last year assignments. So it will be helping you solving the week 4 problems. So if you have any questions, feel free to ask in the chat, or you can just un means you can just unmute and ask the question. Okay. So let's start with the thing. So first of all, we constructed a model. First of all, we know that. Okay, so first of all, we know we were doing something like this in the gradient descent, normal vanilla setting. That is, we were optimizing WT, or I will be using the more general term. Okay. Vanilla gradient descent. So we were optimizing the parameter theta of a neural network. It was a weight matrix or a bias. Okay. So theta t plus 1, the update was looking something like this: theta t minus eta del L with respect to theta t. So this was the normal optimization thing which we were following, where this eta was the step size, okay, and L was our loss, and this is the gradient operator taking a derivative of a loss with respect to a parameter theta t. So we were at initially at this point, okay, we wanted to optimize the function, then we take a step in the direction of a gradient. As taking a will be much, for example, we are given certain functions. Suppose this is a function we are given as, okay, we are certainly theta t is here basically, okay, this is theta t. So what does this mean is that basically we are taking a derivative, that is a gradient, okay. Gradient always points toward a maximum direction where maximum ascent is there. So more common example will be something like this. We are having y equal to x square. Let's take it as 0 as the origin thing, as it will be easier. So we are having y equal to x square. Okay. Now we know that dy by dx is equal to 2x. Okay. If I am at a point x equal to 1, then 2x will be the gradient at that will be 2. So it's telling us that we should move towards 2. That is away from the minima. Minima in this case is 0. Okay. If we are at -1, if we put in the derivative 2x minus x, substitute it to be -1, then it's coming at -2. So it's telling that move away from the minima. So the normal thing is gradient always points towards away from the minima. That's why we are taking a negative direction. We want to move towards the minima, not away from the minima. I hope this point is clear. Now there can be a bunches of cases which can be arising. Okay. So we are following, taking a small step in the gradient, and we are updating our parameter by the small step. So what the role that does this eta plays? So eta is something which controls. So you can think it of as a simple case is that suppose you are driving on an unknown terrain. Okay, there is a road. You have a car basically. You ask some person the direction. Okay, he just told you that go 2 kilometers away. Means just take a 2 kilometer straight. But the thing is that there is a possibility that in between it might not be exactly a 2 kilometer. It might be just 1 kilometer. Okay, because no one knows that at what point of direction what is the this load goes basically. Okay, so when so we can't believe what he's telling that where to go, because we want to go towards the minimum. Okay, so to avoid confusion, we want to make sure that we are moving towards in the direction of minima. Okay, so we'll be taking a small step. The only thing we know is that the person is telling the truth basically. Okay, he is telling that we need to move in this direction. So I'm just saying that yeah, I need to move in that direction. So that's why we are taking eta. Okay, and this del is just as I mentioned, it's the direction towards the minima. Okay, so how do we got this update? Okay, so basically it all came from the Taylor series. Okay, so what is a Taylor series? It's just an expansion of a function with the higher polynomial degree. So it's something like this. I have y equal to x squared. Let's take the same function. Okay. Suppose y equal to x square. Okay, I know the value at this point, suppose. Okay, that is, this is my x1, this is corresponding f of x. Okay, now I want to find the value at this point, that is x2. Okay, so the thing is that if we take a tangent across that x1, and so we can show that the value of this function at x2 should be at least this point. Okay, so which we have calculated based on the information. Let me read out the figure as it will be much more clear for you, I guess. So the thing is that based at a particular point, okay, we have information about the direction. Okay, so it's like we are at this point. We want to find at this particular point. This is x1. This is x2. So if we take a tangent, then I can make sure that function value at this point. I know the function value at this point. I know the location current point. I know where I want to go, x2. Okay. I want to know that what's the value of f of x2. So the thing is, if I take a gradient across x1, then I'm pretty much sure that this function value should be at least this by the linear approximation. We are kind of doing an approximation of x2 around x1 by a linear line. Okay. Now also I can take a parabola y equal to x square. If I add a term much more, that is x square, then I'm much more pretty much confident that my function value should be this, the next one. So like that, if I add a bunches of function y equal to x cube, y equal to x4 till infinite, then this sequence of a function will converge to f of x2. I hope this point is getting clear. So this is what the Taylor series tell intuitively. Okay. So basically we have a loss function which depends upon theta. Okay. It's a function which takes the argument theta. So function is dependent upon theta. Okay. Now I want to update my theta to theta plus eta u. U is my direction in which I want to go. Okay. I don't know in which direction to go, because if I am at lost curvature, okay, any lost landscape, I don't know where to go because there is a lot of directions. I wanted to find the optimal direction basically. Optimal in the sense that if I follow that direction, I am pretty much sure that I am decreasing the value of my loss. That's what you want in the optimization. Okay. So let's do the Taylor series approximation of theta plus eta u around theta. So it will be looking something like this. Theta plus eta u is equal to L of theta plus eta u transpose del of L at theta, which is a function of theta. Okay. Then again, some functions of higher order of eta square will be coming. Suppose eta square is very small because we are moving very small pace. Okay. So this whole term actually is not needed. Okay. Because it's a very small quantity. So the linear approximation tells us that if I know the value of L theta, if I follow a direction, then this is the equation which is getting followed. Okay. Now the thing is, I suppose L theta, I take it on the left hand side. Okay. L theta plus eta u minus L theta, which is equal to eta u transpose del with respect to theta of L of theta. Okay. This quantity is basically I am at a theta point. I want to take an upgrade to the next step. I want to make sure that my means in decrement, means I want to decrease the loss value. Okay, so this whole quantity should be less than 0. Okay, so then if this quantity is less than 0 and this is a vector, basically u transpose del theta L theta is just a dot product. Okay, and the normal dot product, now you can write it as u transpose eta is just a scalar quantity, so we can just remove it. So this quantity we want it to be negative. This is negative, as we know that v transpose u can be written as magnitude of u, not magnitude of u cos theta. The theta is the angle between v and u. This quantity is negative if theta is cos theta is negative. Cos theta is negative only between from from pi by 2 to minus pi 3 pi by 2. Okay, so this theta should between that. And what's the maximum value it can attain is when these two vectors are, the angle is maximum. That is, the angle will be maximum. It will be maximum when both of them is aligned in the same direction, and it will be minimum when both of them will be aligned in a different direction. So if v is my this direction, u should be opposite. So in that case, cos theta will be negative. I want a maximum decrement in my loss. So this can be expanded, written as mod of u, mod of del theta L of theta cos theta. Okay. So this quantity, I wanted it to be negative, as I mentioned. So the theta will be negative only if, so this quantity we wanted to be negative. Okay. This quantity will be negative only if my this L theta, this direction is given to us already. Okay. And we wanted that to follow in the direction of that, means this u was unknown. We wanted to find the direction u. Okay, so we wanted to find the direction u, and the key thing we had is the cos theta. It's just a control in our hand which we want to use it to tune the value of u in which direction we want to go. Okay, I hope this point is clear for you guys. Okay, so I'm trying to follow as much as the notation as was used in the weak lecture, so that it's easier for you to follow the same notations thing. Okay, so yeah, so so this was the theta. So u we will be taking as negative L theta. So this is the direction we want to take. So that's how we derived this equation of the gradient descent, theta t plus 1 equal to theta t minus eta L with respect to theta of L of theta. But just tell us that if you have a particular point, do the linear approximation of that function at that particular point, and they take a small direction towards that linear approximation. It might not be the best thing to do, but yeah, it's one of the approximation. Means we are means at all the point we are make sure that that we are decreasing the value at least, not it should not increase basically. Okay, and also this cos theta we took it as 180°, in which case the cos theta will be -1. Okay, so all one thing is always remember, you need to move in the direction opposite of a gradient. That's a golden rule. All the optimization algorithm to some or the other extent use the same rule, irrespective of whatever algorithm you are using. There are some, this all thing is based on taking a gradient. Like taking a gradient, we can take a gradient of a gradient. That's a Hessian second order derivative methods. but that's kind of a means computationally heavy. Okay, but there are certain algorithm which is parameter free, so that is not as much accurate as this gradient descent thing. But yeah, that's kind of some heuristic. So if heuristic which people are using in some areas of research. Okay, so the intuitive explanation of this gradient descent, you can think it of as we are at this particular point, we are just taking a small step, we are moving here. Okay, until we reach the minima. But the thing is the theta value. The theta value actually, suppose I know that I want to go 1 kilometer ahead. Okay, and if I take a 100 steps, okay, 100 meter 100 meter steps, then that's quite a hectic process. Okay, hectic in the sense I am going moving towards the minima, taking a small step, but I want to reach the minima as soon as possible in the less time. Okay, if you want to reach from your home to the school, you want to follow a path which, because your walking speed is constant. Okay, you want to find a path which minimizes your time. Okay, some paths you can follow, you can always reach your home. That's not a case, but you want to reach your home as soon as possible. Okay, so for that you need to tune the speed. There might be a zigzag. Okay, so how to follow that? So the eta, if you take small step, then it will be something like this. If you take eta very big, then you might be crossing your minima. Okay, so like this something, some oscillate. You'll be doing an oscillation around the minima. Okay, this is not we want. Neither we want the slow convergence, means moving very slowly towards the minima. Neither I want to move very fastly towards the minima. Otherwise, I am gonna decrease my value. Means there is oscillation that I don't want. So there lies a sweet point of taking an optimal eta so that I reaches the minima in the minimum time as well, and I don't oscillate so much. Okay, and also this gradient descent, it all depend upon the gradient. Suppose my graph something suppose looks like something like this. If I am at this point, the gradient at this point is particularly around zero. Okay, I know my minima lies here. If I take a very small, my gradient is also small. If we take a lot of, I'm not even sure that whether I can able to reach here or not in the fixed amount of time. It might take an infinite amount of time to reach the minimum. Okay, so at some point the gradient value will be very low, approximately equal to zero. Okay, so we might get stuck in the means flat, very kind of a stuff. If at certain point my slope will be very high, like in this case, suppose, okay, in one step lot decrement will be happening. In another case, it will be, as I mentioned, very low. Okay, so it all depend upon the gradient. Gradient plays a very important role, but sometimes just follow the gradient blindly is not that much as useful as because as I mentioned, no, just if the gradient is very high, we'll be moving means very steeply towards the minima. If gradient is kind of a very flat, where the gradient approximately is equal to zero, then we'll be moving very towards very slowly. Okay, so the question arises, can we do better? Okay, so this is the main question. So the thing is, gradient, it conveys a lot of information, not just about the direction we want to convey. So suppose, as I mentioned in this flat region, I know my gradient will be pointing towards some direction. Okay, suppose it's like this. Okay, I took a next step. It's also pointing towards this direction. Okay, so it's like this. As I mentioned, I want to go 5 kilometer ahead, but instead of directly following 5 kilometer, I will be again 10 meter. I will be asking a person where to go, where to go. Okay, It's a time consuming process, but yeah, we be reaching the minimum. So, but suppose that means I am at a particular point. The guy told me that go 2 kilometers that direction. Okay, but I took 10 meters. Again, I asked another person. He told me go 2 kilometers, something like that. Okay, so both of these people are telling kind of the same information that the direction is the path on which I am as of now is kind of a correct, because two-person are telling the same thing. Then there's a more probability of having path, whatever they are mentioning me. Okay, so I will be following that. Next person I'm asking, again, he is telling the same thing. I will be following that person path. If he tells me the different thing, I need to think. The previous person told me this direction, this person is telling me that direction. What should be the ideal direction? Okay, but yeah, if we take a previous person information as well, I am little bit much more confident towards the decision to make at a particular point. Okay, so that's where the momentum based gradient descent come. So by the name momentum basically, as I assume that you might all of you are the science students and you might have seen the Newton of equation that momentum is mass into velocity. Okay, here the velocity is just a gradient, the mass. Okay, so there is a relation between the force equal to ma and the kind of thing we are gonna derive here. Okay, so momentum is something that the previous person is telling me some information, the current person is telling me some information. I want to combine the both information to take the decision at the next point. Okay, so I am at this particular point. He told me that go this direction. Okay, this person A, the person B is telling me go towards this direction. Okay, now if I am here, I want to update my weight rather than just believing the person B. I'm gonna take the information of person A and combine both of their information and try to take a mean kind of a means average kind of a path. Okay, so it's like this. This person is telling me this side go, other person is telling me this side go. Okay, I will be taking this. I will be following this direction. Okay, so that's the only thing. I have momentum basically means the previous person is also having a important role in making a decision at next point of time. Okay, but the thing is we can't equally here means as for example, if we started with the point something here, I had one expert, went second expert like this, nth experts. Suppose all the people who are telling you to go do this direction, they are all expert. With the time I am listening to the most, I should listen to the most recent expert, kind of most recent person, and I should also give an average to the previous person as well, but not much, because as I am moving forward, I want to use the information about my past at 100 second back or 10 second back. I want to give more weightage to the person who recently told me that follow this direction rather than the person who told me 100 seconds back. Okay, so the thing about the gradient descent is that we are means the update use how it is getting defined in gradient based momentum based gradient descent. MVGD, momentum based gradient descent is just a short form I wrote it. Okay, so it's like this: update at t depends upon the gamma of update t minus 1 plus eta del of L, then theta t plus 1 is equal to theta t minus update t. So here, if you see the logic, this update is always remaining the constant because we are at particular point, we need to follow a direction. So this is the same convey, meaning whatever optimization algorithms you see or you do, this thing remains the same as we are solving a differential equation. Basically, this is just a discretized version of a differential equation. So let's not come up to that. Update T is telling us that I am giving the weight gamma to the previous direction, what the update was, and I am following the gradient at that particular point. So as I mentioned, we are listening to the previous person by the gamma. The next person go here. I will be taking a net combined direction. Okay. So this was kind of it's a kind of a, we have a ball, we have certain slope. Just remember the mass. So the velocity along the slope is mg cos theta. Okay. As the angle get increases, the momentum should increase. Okay. So that's what the main objective of taking this momentum based gradient descent. And empirically, it performed better than gradient descent because that is what expected. But the thing is, there is a kind of a lot of oscillation as well here. Oscillation means because we are listening. Suppose there is a certain turn. Now, previous person told me go 1 kilometer, 10 meter, and after 10 meter, after 20 meters, okay. The next person told me also to go 10 meter, and after 20 meter there is a turn. Both of them, if I combine it, okay, I should basically means I will be getting the oscillation. I might end up going beyond that. Okay, the normal trajectory which I wanted to follow. Okay. So that was the main thing of taking this momentum-based gradient descent. Okay, I hope this point is clear. So basically, now one more thing I wanted to discuss, I forgot about is contours. So as a human, we only understand is 2D plots, 3D plots maximum. We can't visualize the higher dimension plots. Okay, and also we are much more comfortable working with 2D plots. Okay, that's the thing. Okay. So in the higher dimension, we can't visualize it. If we were able to visualize it, then machine learning would be much more easier in that case. The only thing with the machine learning is that as the dimension get increases, it's out of our control. We can't visualize it. We don't know what is happening. Okay, that's what the whole deep learning is all about, solving a higher order dynamics. Okay. So contour is one of the method in which we take a 3D plots and try to project on a 2D. Okay. So suppose I have a function something like this. Okay. The thing is, it is in the 3D. Okay. Here I am having a very high value. If I take a slice, very small slices across the y-axis, and I project across the x-axis. Okay, this is just a doom in the 3D. It's not a 2D actually. I'm taking a slice of a hyperplane, try to cut it into a small bunch of thing. Then I can, on the 2D, the same lines of bunches will look something like this. Okay, so the more concerning the circles are, it's just showing the change of values in the 3D, how it is happening. Okay, and it's much more easier to work with this kind of a plot or visualize it, because as I mentioned, in 3D or higher dimension, it's the dynamics and visualization of as a human perceive is get harder and harder. Okay, so the optimization algorithm, basically what it does is that we want to reach minima. Okay, so we start with certain points. Okay, so this is the contour basically. The higher values are denoted by a darker regions, means it will be much more darker, and lighter regions means minima kind of stuff. So suppose if we have certain some contour like this. where this is a minima basically, not some maxima. Okay, don't get confused with the notation I'm following. Okay, so basically in optimization, we are at a particular point. Okay, and we take a direction. We want to move towards the minima. So this is a trajectory. We want to make a trajectory basically, okay, to reach the minima. That's what we want. Okay. So all the optimization algorithm, we are at one particular point. At one particular point, the information we are having is the current location, the current function value. We can get the nearby approximation of this function by taking Taylor series. Then we try to find the best direction to take it. Okay, so all the optimization, this concept remains the same. Okay, but the direction we are taking, it's kind of a means depend upon the gradient descent. O- Okay, so how much we want to move ahead, with what step we want to move ahead. That's what the different optimization algorithm try to formulate. Okay. So I guess in the lecture series, you might have seen a lot of different kind of a different contours and the trajectories as what I can see in the lecture material. Okay. So if someone who has not went through the lecture material, please follow the lecture material. Okay. As of now, as I'm assuming that you have already went through, so it's just a revision so that whatever is needed for solving the assignment, we have order tools available with us. Okay. So yeah. Now the thing is we are gonna be covering is about uh, mini batch gradient descent and stochastic gradient descent. It's just a variation of normal gradient descent. Okay. So the thing is, uh, normal gradient descent you already know. Okay. And if you perform a normal gradient descent, taking a small value of eta, there is a probability that you will be reaching the minima, but it takes a longer time, and you are making a one update on the calculating the gradient with respect to all the data points. Okay, and sometimes it's not as feasible as what we wanted, but you want to make more frequent updates. You want to reach your minima as soon as possible. You want to make it computationally less heavy. Okay. So the question is, can we do better? Because, for example, ChatGPT, simple thing. Okay, it has been trained on a billions of data, billions, trillions of data all over the internet, everything. Okay, and taking a gradient with respect to each and every data is, and just to update once, it's kind of a very computational wise, it's very poor choice or poor algorithm. Okay, and also on one GPU, you can't fit this. We don't have a GPU which can fit all this large storage of data. Okay, so the question is, can we do better? Can we reduce the computational complexity as well as more in the lesser time to reach the minima more frequently? So the question is, the answer is yes, we can. Okay. So so guys, if you have any question, feel free to ask in the chat bot, or you can just unmute yourself and ask it. Okay, don't hesitate. So the thing is, we are having at a gradient descent. This is just a contour plot. Okay. Normal gradient descent, where we take a gradient with respect to all the bunch of datas. So there is something called stochastic gradient descent. Stochastic gradient descent means is that with particular, I see, gradient is with respect to the we are taking expected value of a gradient. Okay, this expectation, we just write it as 1 by n equivalent. Expectation means we're taking averaging the gradient over multiple data point, then we take a direction, which is 1 by n summation I equal to 1 to n del theta of L of loss, which depends upon x of I. Okay. So this is a Monte Carlo approximation of the gradient in the normal gradient descent. We take a gradient with respect to all the variables. But if you take a gradient with respect to just one point, in the expected sense, it's equivalent to the normal gradient descent. I hope that this point might not be clear for someone, but the thing is, the whole descent we are doing, del theta, it's the expected value of with respect to all the grid data points. But if I am at particular point, I calculated the gradient, I'm taking a gradient with respect to all the data point, deciding my direction. But suppose if I take a gradient with respect to just one data point, because 100 data points are there. In normal gradient descent, I need to compute a gradient of 100 data points, take a summation of it, average it, then follow one update. But if I have 100 data steps, 100 data points, I take 100 updates, I can do it. Okay. So with normal, we can take 100 steps, basically 100 in this case. So can we make sure in this case, we are also decreasing and it's much more faster in the expected sense. So that's what the stochastic gradient descent is. So in one step, in one epoch, you make total n, where n is my data point, n number of updates, which is much more better than one update as compared to normal vanilla gradient descent. But the thing is, taking gradient with respect to one data point, it will be noisy. We want to minimize over all the data sets, all the data points, not with respect to one data point. So the question is, can we have something, this will be very much oscillations will be there. Okay, this is will be smooth. So can we do better to take the advantage of both gradient descent and the stochastic gradient descent? The answer is yes. We can construct out of this n small batches. Batches is just, for example, 100 data points are there. I can make a batch of 20. So total 5. I am dividing 100 into a bunches of 5 bags of 20, 20, 20. That's the batch size. 20 is my batch size. Okay. And if I take a gradient and do the summation and average over this 20, it's a better. I'm taking advantage of this smoothness and making a 5 update. So it will be lesser oscillatively. So that's how the mini gradient descent is defined. Okay. So the number of updates we be having here in the normal mini batch gradient descent. Don't get confused with the momentum based gradient descent. It will be n by b, which is also better than 1 in vanilla setting. Okay. So yeah, so I guess we have covered this point. Okay. Now let's the thing is the about the step size. Let's come to step size now. Okay. So in the step size, the question is about as our total thing is theta. Let me use the same notation. Theta t plus 1 is equal to theta t minus eta. Then some update we were doing here. It will depend upon the algorithm, the moment. So certain term is there. I'm trying to avoid because it depends. can be a negative of a gradient, mini batch with respect to one data point, momentum based considering the previous updates and all. Okay, so the form, but the form remains the same everywhere. It's not gonna change. We are having theta t plus 1 equal to theta t minus eta with certain direction u, suppose. Okay, this is u. Okay, so the thing is, this theta basically, if initially, as I mentioned, if you take a very small, you will be making a very small data step means update. But if you take a very large, you will be oscillating it. So see, whenever you see a two extreme cases, and either both of them are not feasible, okay, so you want to have an advantage of both the thing. See, you want a, this is better because it's update a little bit better, faster. Okay, but it oscillates a lot. This is smoother. The question again rises here is that can we do better? See, in the optimization, whatever algorithm you are having, question always remain the same. Can we do better? Okay. So the answer is yes, we can do better. Okay. So the thing is this eta. Initially, let's take a very large steps because initially will be very far away from the minima. Okay. Then as soon as you reaches around the minima, okay, take a small step. That's the way we can means initially we are making reaching towards the minimum faster as well. And once we know that we are within certain epsilon ball or we are means certain distance from the minimum, we can take some small steps. So that's how there is things for doing that. Decay, step decay is there. Okay, we are having an exponential decay. I guess this all things are covered in the materials. So those who haven't went to the material, just go through it once. So in the step decay that after certain epochs just reduced by the half. So for initial it will be eta by 2, eta by 4, something I can have. Exponential you can increase, make eta as a function of step size update t, and decay 1 by k. There's a lot of different things. So you can just look into the content. Okay. So I hope up to this point it's clear. Okay. So let's take 1 minute of break and again come back. Okay. Welcome back, everyone, again. Okay. So I hope until this point everything is clear to you. Okay. So see, the main purpose of doing this exercise is basically for you to means get familiar that what's the concept you need in solving the problems. So these are some of the concepts which I felt that in the assignment it might be needed for you, okay, or to have a revision, okay. So yeah, now we'll be coming to the gradient descent with adaptive learning rate, okay. So adaptive learning rate, gradient descent with adaptive learning rate. So what's the intuition behind this thing? Means normal gradient descent we know, but what is this adaptive learning rate? So it's talking about the eta thing. So can we make this eta update dependent on the previous update history? Okay. So the question it's asking is like this. I was at this particular point. I the gradient it gave me was suppose this point. Eta. Okay, let me read it again properly. I'm this particular one. I want to update. Okay. I know that what's my loss here, what's my position here. Okay. In this case, it's kind of a convex function I took purposely, so it's easy. Otherwise, I can have something like this as well. Okay. So the thing is, the learning rate will be taking it this much forward. So the loss at that particular point will be this. Okay. So can this eta step which I'm taking, okay, can I make it better on this update, that how much update is done? Because if you see, if it's something like this is there, initial it will be very much high, there will be a sudden decrement, then if I make an update it will be very small. So that you can see the normal gradient descent, if you take a very large high gradient, then again low is this. So if you make a eta dependent upon that, what we are at a particular point, what's its update history, means from where we are coming it. So can we do better? The question is that only basically. It's the same over all over the optimization. That to make a better and better and better optimizer, make it converge faster and faster and faster. Okay. So the thing about the ADA, so that's where the ADA grad came. In the ADA grad, it was something like that: VT is equal to VT minus 1. Okay. Yes. Some term del L square. So del L square is the gradient. We took a purposefully square because we want to make it non-negative. That's the thing. So the theta t plus 1 is equal to theta t minus theta divided by v of t plus epsilon del L. The thing about this epsilon is that we want to make sure our denominator is well defined. It's a very small value, nearly equal to 0. But that's only thing we have is to make sure that this denominator is well defined, because if v of t at some point or numerically in the computer is 0, then this epsilon will make sure that it does not equal to 0. Means because 1 divided by 0 is infinity. Okay. So to avoid that instability, otherwise it's the same. So what we are telling it here is that we want to move towards in the direction of the gradient with the step size which is proportional to the velocity, or you can have with the update history. Okay. V of t you can by default take it to be 1. Okay. So the thing is, as initially the V of t will be means high the gradient. See the how it will get saturated as we be moving slowly and slowly. This we as we are moving towards the gradient. Initially, the gradient will always be higher. Basically, if you meaning reaches the minimum, gradient tends to 0. Once it's so initially this term whole term will be higher. If this is higher, 1 divided by higher, we are gonna make a small step. Okay, if my gradient become lesser, this term will be decreasing. 1 divided by lesser term will be higher. So we are moving much more faster. So that's the thing about having this update. Okay, so based on that, the thing is this d means this thing it's depend upon the L square. Initially, as I mentioned, gradient will be higher. 1 by higher, initially it's hardly updating. After that, as this denominator will be increasing with time, then this term will be very much larger step. It will oscillate a lot. I hope you are getting it, what I meant to say. Initially, Vt as del of L will be higher initially, okay? Then it will be much more higher, okay? But the with the time, as because see, 1 by something is there. If something is higher, the update is slower. If something is slower, then the update will be higher. Okay. So there is a very aggressive learning rate in the adaptive. So the parameter started seeing a very small update because of decay learning rate with the time. Okay. So that's where the RMS prop was proposed. See, this is I'm doing just an exercise of what was done in the week lecture. Okay. So if we are not following what this all algorithm does is just go through the lecture once more. Okay. As an IDA candidate, I will be just telling you if you are new to the field, try to watch the lecture first time. Try to watch the lecture. Okay, understand it. Take as much time as you want in learning it. Try to attempt the question. In the question, if you feel that you don't know something, again watch a lecture, again solve it. So this is an iterative process you need to do if you want to make your concept strengthen. Okay. So in the RMS prop, they did a very minute change. The update will remain the same, but the VT they changed it as VT minus 1 as 1 minus beta del of WT whole square. So beta. So the thing is, this beta now controls that the gradient. It, in this case, it's for us. I'm using del of L. So let's use it the same thing. Okay. See, don't. I'm using a little bit different notation. Try to make it as much the same notation what was followed in the lecture at theta t basically. Okay. So this beta 1 minus beta, if beta is very higher, then it's giving a very small weightage to this thing. Okay. If beta, if you take 0.9, okay, then this will be giving a smaller weightage to this. Then it's controlling the stability. Okay. So the eta was something like this. We defined it as Vt plus epsilon. Epsilon, why we added, I told you already. The main purpose, you are already familiar with that, why we need epsilon and V of t. The beta thing is to control the regress change in the denominator. And it was showed that this is a little bit much more, the update was proper because, for example, if you have loss curvature where across one dimension the loss varies a lot, across another dimension the loss does not change. Okay, but the update will be along the one direction in which you'll be just wasting a lot of time. You want to make an overall update. So that's the thing of having a beta. Okay, so beta will make sure that you are updating it properly. Okay, but there is now you might have seen that this V of t, it is taking the information from the previous step, try to accumulate it, but there is always a decay with the step. Decay in the step is beta times the, for example, it is like this. V of 1 is equal to beta B naught plus 1 minus B. Suppose this I take as C1 and try to take it as a C1. V2 will be beta V1 plus 1 minus beta C2. Substitute 1 into basically it will be V2 is equal to beta square V naught plus beta 1 minus beta V1 plus 1 minus beta C2. Okay. So this beta square, if we take beta as, because as I mentioned, beta we take as a larger, with the time, if you see that the decay, this decay will always be there with the time, because 1 minus beta is there, this odd term. So it's kind of, you can see, it's giving more weightage means to the previous update as well, because beta 1 minus beta, as beta is ranging from 0 to 1, so beta into 1 minus beta is it will be lesser. It's giving more weightage to the latest update, but this thing weightage does not decreases rapidly. So there is a decay issue here as well. Okay, so that's why the Adam was proposed to solve the issue it was having in this RMS trauma ADA. So they have defined the mass velocity like we have force equal to ma. So the thing is basically m of t, they defined it as beta 1 m of t minus 1 plus 1 minus beta 1 del of L. Okay, V of t is the velocity, beta 2 Vt minus 1 plus 1 minus beta del of L whole square. Del of L square is kind of a good we want because it's not negative. That's the main thing. Okay. And this is the normal update which we saw in the momentum based or nested accelerated gradient descent. Okay. So it's just trying to use the previous algorithm. Why they have used that particular term? They try to incorporate the mass. M basically means the mass. V is the velocity. So on the slope, we have a ball. It's having a mass and the velocity. So the next point at the ball always follows the means because the gravity is there. Gravity wants to do the least amount of work. It will always follow the bar which is least. So that's the main objective. So if you're from the physics background, you might have seen this mass, velocity, and all. So then we define m of t as m of t divided by 1 minus beta of t, where beta is kind of 0 to 1. So with the time t tends to 0, t tends to infinity, this term goes to 0. Okay. V of t cap is equal to V of t divided by 1 minus beta t, beta 2a. It's beta 1, beta 2 of t. Okay. Okay. So the update is basically looks something like theta t plus 1 is equal to theta t minus this eta divided root under Vt cap plus epsilon into m of t cap. So this is again a step size which depends upon the time of the update, and this m of t is the direction. Whatever the optimization algorithm you see across the machine learning, controls, engineering, everywhere, this form remains the same irrespective. Okay. Only the thing is people are designing more and more controls, more better, which converges faster. Okay. So that's the thing I have tried to cover that. What I say. I tried to cover the concept of uh, this week. Now let's solve the week for last year questions. Okay. Week 4 assignment. Okay. So the first question: which step does Nesto accelerated gradient descent perform before finding the update size? Okay. So the question is, which step does Nesto accelerated gradient descent perform while finding the update size? Okay. So the options are increase the momentum, estimate the next position of the parameter, adjust the learning rate, decrease the learning step size. So in the nest of gradient descent, as I mentioned, it calculates the gradient at particular point. Okay. And the new position is determined using this. It estimates the next position of one parameter and calculated the. So first of all, we had this parameter. It calculated the update step. Then again, we take follow the direction, and then we try to combine and take an optimal step for that direction. So it's looking into the future update and try to update it, the parameters. So the answer is estimate the next position of the parameter. Let me rewrite it properly. That estimate. The next position of the parameter. So in the nested gradient descent, it estimates the next position of the parameter and calculates the gradient of the parameter at that particular position. And the new position is determined using the we are at particular direction, then gradient, the next step gradient, then take a combined thing. Okay. So that's the first question. Select the parameter of vanilla gradient descent. Okay. Controls the select the parameters of a controls the step size in the direction of the gradient. See, they have asked select the parameter of vanilla gradient descent, the normal one, which was stated in the previous week. Controls the step size in the direction of the gradient descent. So we are following in the vanilla gradient descent. We take a gradient and try to follow it. So we have a parameter eta there. So the option is learning rate, momentum, gamma, none of the above. Answer is learning rate. We have defined the eta. Answer is learning learning rate eta. Okay. So this question is very much straightforward because normal vanilla gradient system, we had a eta, we had a gradient. gradient is the direction, eta controls the step size. That's it. We have a learning rate. Now the third question: what does the distance between two contour lines on the contour map represent? So it's asking this thing. We have certain this contour plots. So these two lines, what does it represent? What does the distance between the two contour lines of a contour map represent? The change of the output of the function, the direction of the function, the rate of change of the function. None of the above. So basically the contour plot, as I mentioned, we in the 3D, if we are having, we take a size. So one size or the function value we be having. So one line indicates they all are the same values. Okay. And another size indicates the different values. Okay. If 2 points are nearby means values, it shows us the, what I say, the steepness. Okay. So we are having a steepness. It's also, we know the value of both the point. So the answer is rate of change of the function. Okay. Fourth question, they have asked us to represent the contour plot of a function. That's a pretty much good question. Okay, we'll be solving it. I will be just telling you how to have a contour plot. Okay. So f of x comma y is equal to x square minus y. Okay, so it's a 2D function. We are having x, we are having a y. So basically it's in 3D. At 0 comma 0 we are having 0, so certain function it looks like in the 3D. It's not exactly the same, but it's something. And now we need to project it back to the 2D thing. Okay, so four different means four options are given, and all the options are given from basically the domain -4 to 4. Okay, so the thing is this function is there. Okay, so I have need to draw a contour plot -4 to 4 basically domain -4. This is x, this is y. It's also between -4 to 2. Okay, now if x square minus y, okay, suppose my x square minus y is given. Okay, so see the trick for solving this kind of a problem is, first of all, x square minus y is given. If y is 0, suppose, okay, my function will look something like x square only. Okay, if y is 0, my function is just x square. If x is 0, my function is just minus y. Okay, so if x and minus y is given, okay, so if my, as I mentioned, if y is 0, okay, if my y is 0 and okay, so first of all, draw 0 comma 0. Okay, along this is 0, this is again 0. Okay, if my x is 0, this line is kind of a minus, it's kind of a maintaining the common balance. If my if x is 0, this is again a straight line. Its value is again straight line. Okay, so in the multivariate calculus, okay, if it end at 0 comma 0, it's 0. Okay, at 0, 0, it's 0. Okay, and this whole function will be 0 if x square is equal to y. Okay, if x square is equal to y, so between the domain -4 to 4, if my 2 is there, so it will be like something like this, where this will be 2, this is -2. This is the equation of x square equal to y, and this function value is 0 throughout this point. Okay, now if x square is equal to y, okay, now my x, I just keep it. I know the shape something looks like. See, as function is continuous, there won't be a drastic change. Okay, so suppose I keep x as 0 at similar, and the y, it will be just a constant line. Okay, this, and suppose, okay, and if I keep y constant, y is certain, so for example -1, y is suppose 1. If my y will be 1, then my function will be x square minus 1. Okay, its value will be 0 at y is equal to -1. Y, x square equal to y just keep it as 1. Okay, so we have something like this. This is -1, -2, -3. Okay, if I am keeping y as a -1, then this is a y square. This is just a shifter. Just keep y constant and just see how the value will be getting. If y is my constant, and I need to have a constant value, x square -1. So see, x square equal to 1. If x square equal to y, then this is the line I'm getting it. The whole value is 0. In the contour plot, one whole diagram represents the same value of a function across that thing. Okay. Now, if x, I just keep at this point, suppose I'm at this point. Okay. Suppose x is 0. X is 0, y is -4. Okay. Minus of -4 is just 5. Okay. And x is equal to 0, y is equal to 0. See, the one thing you can do for this kind of a problem is just calculate the value, means create a bunch of boxes, just create a mean value and just draw it. That's a direct trick. But here what I want to tell is basically I want to draw a curve which is the same value across all the point. Okay. So if my y, I just keep it as, sorry, okay, if I keep x as x as 0 or y as -5, as -5, x is 0, then it will be -5. Okay, and -5, it will be x squared minus y is equal to 5. Then x squared is equal to y plus 5. It's just a shifted version of 5. The curve will look something like this. Actually, see, the trick is make it this at some constant value. X squared plus y, no, x squared, sorry. See, the simple thing of drawing the thing is, as I mentioned, there's the two things. First of all, x squared, you need to have a constant value throughout. So throughout means in the sense it x squared is equal to y plus c. X squared plus 4. And if you want to draw it, okay. If c is 0, and so this whole value will be 0, it will be something like this. If c is 1, okay, it will be just a little shifted version. If c is 2, something like this. Okay, so this is what the contour plot. So option in this case is will be B. Okay, see, in the contour plot, one line represents the same value. So whatever expression you are getting, equate it to a constant and then solve it, plot it. The constant treated as a constant. Okay, so that's the trick. Now the fifth question: what's the advantage of using ADAGRAD over other optimization algorithm? The option is it converges faster than optimization algorithms. It is less sensitive to the choice of parameters. It is more memory efficient, and it is likely to get stuck less likely to less likely to get stuck in local minima other than other optimization algorithm. So in the ADAGRAD, basically the main purpose was we were tuning the eta parameters. Okay. So the main purpose of using the ADAGRAD is that the running parameter it's dependent upon the weights on the gradient history we are having it, which is make it less sensitive to the hyperparameter eta. By default, we define the hyperparameters. Okay. So hyperparameters are the parameters which you define by default whenever you are running the algorithm. So for example, eta equal to 10. So we want to make it less sensitive dependent upon the eta n. So the answer is it is less sensitive to hyperparameter. Okay. And it can be very much useful in the higher dimensional data set complex model. Okay. Where you don't know what's the ideal parameters. So basically, you want to design an optimization algorithm where the initial condition should be independent of that. So that's why the ADAGRAD was proposed. The sixth question. We are training a neural network using a vanilla gradient descent algorithm. We observed that the change in weight is small in successive iteration. What is the possible cause for the following phenomena? And it's a multiple choice question. Eta is large, del W is small, del W is large, eta is small. So it's telling that means we are updating the parameter that is theta 0, theta 1, to theta n. Okay. And the weights are not getting means very small change. They are not getting changed means by a large amount, very small. So the theta n is equal to theta n minus 1 minus eta del of theta, del of L. Del of L. Okay. So the reason is that the difference between theta n and theta n minus 1 is not getting gradually changed is because eta might be very small. Okay. And the second reason is that del of W is small. Okay. So that's the simplest thing. So the answer is the small update signifies that the quantity eta LW is small. It happens only when each individual is small. Okay. So sixth question is done. Now the seventh question. See, whenever you try to attempt questions, make sure just write down everything you know about the questions and then solve it. You just need to plug and play around it. That's the only thing actually, all the assignment questions. You are given a labeled data, which we call X, where the rows are the data point and columns are the features. So X is given, it's in the form of R, N number of N is the number of data points, and D is the features. Okay. One column has most of its values 0, and so one feature is most of the values 0. So it's with respect to that, the gradient will always because is 0 kind of. Okay. What algorithm should we use here for the faster convergence and achieve the optimal value for the lossy problem? The options are nested accelerated gradient descent, ADAM, stochastic gradient descent, momentum based gradient descent. So one of the way vector is sparse. Okay, so the answer for this question is Adam. The Adam which we made sure that it does not depend upon the input features basically. That's why we had a mass. Okay, the moving averages in the Adam are initialized as a zero. Okay, so the Bara's first and second order gradient it takes. So it always collect the averages between the next point with the and the next update with the previous updates and all. So the estimate of the gradient update is much more proper in that case. So the answer is Adam. Now the eighth question is, what's the update for the Adam? So the normal update tool for the Adam was basically theta t plus 1 is equal to theta t minus some L learning rate, which was adaptive, root eta divided by root of v of t plus epsilon, okay, times m of t, okay, divided by root of vt plus epsilon, okay, vt plus epsilon, yeah. So that's the normal thing. So it's directly from the question. Now coming back to question 9. What's the advantage of using mini batch gradient descent over batch gradient descent? Okay. So the advantage of using a mini batch gradient descent over a batch gradient descent is that it's much more computationally efficient. Basically, it allows the parallel processing. We can take a different batch, take a gradient update on a different servers, and make it much more faster. And it converges better than batch gradient descent. So as I mentioned, batch gradient descent means they are talking about the linear thing. So the correct option is mini batch gradient descent is computationally efficient than batch gradient descent, and mini batch gradient descent converges faster than batch gradient descent. Faster and computational. Okay, computational efficient and faster convergence. Okay. Now coming back to last question, 10th one. Which of the following variant of gradient descent that uses an estimate of the next gradient to update the current position of the parameter? I already answered this question back. Okay. The answer is nested gradient descent. We are at a particular point. We take a gradient, and in next point, before updating the parameter at a current state, we look at the gradient for the next update as well, and then take a combined decision. Okay. So the answer is nested accelerated gradient descent. So guys, yeah, that's all for the today's session. I hope you enjoyed it. So if you have any question, feel free to ask in the chat or put it around the put in the group, or we have a Google groups there, so you can put it there. So thank you guys. I hope you enjoyed the session.